Tisztelt Hölgyeim és Uraim! Nagyon nagy szeretettel köszöntök mindenkit a harmadik osztály, a matematikai osztály ma délutáni esemény sorozatán, aminek a fókuszában a mesterséges intelligencia lesz. Na most a mesterséges intelligenciáról tulajdonképpen bármilyen weboldalra tévedünk, egy pár másodpercen belül értesülünk, mindenféle segítséget kínál fel a számítógépünk, a mobiltelefonunk, a kávédarálónk és a hűtőgépünk, hogy hogyan éljünk a mesterséges intelligencia által biztosított lehetőségekkel. Nekem mégis sokkoló volt a Svejtszer verseny megrendezése kapcsán az, hogy mikor a verseny véget ért, ugye nem kell elmondanom, hogy mi az, hogy Svejtszer verseny. Ez 10 napon keresztül 10 feladat megoldásáról szól. Most a Svejtszer verseny utolsó napjaiban a ETH-ról, a Mataréna kutatócsoporttól érkezett egy megkeresés, hogy ha hozzájárulunk, akkor megoldanák ennek a versenynek a feladatait a mesterséges intelligencia segítségével, és néhány óra leforgás, először elkészült egy angol nyelvű fordítás, aztán néhány óra leforgás alatt megkaptuk, a verseny végét követően megkaptuk a mesterséges intelligencia általi megoldásokat, és el kell mondjam, hogy a 10 feladatból 9-et hibátlanul oldott meg a ChatGPT 5 Pro nevű mesterséges intelligencia szoftver vagy platform. Nem tudom ezt minek kell nevezni. Szóval ez elég sokkoló volt számomra, én ezeket a megoldásokat elolvastam, és hát meg kellett állapítani, hogy a 5 éves matematikus képzésnek a tananyagát készségszinten kezeli a ChatGPT Pro. Tehát minden, amit egy 5 éves matematikus a matematikus képzés során elsajátít, az rendelkezésre áll, és kreatívan alkalmazza ezeket az ismereteket. Szóval ezért gondolom, hogy Szegedi Krisztiánnak az a megállapítása a székfoglalóján, hogy a mesterséges intelligencia már biológiai szempontból egy olyan 24-25 éves PhD fokozattal rendelkező kezdő matematikus kutatónak a színvonalában, ez nem túlzás. Hát azt gondolom, hogy sikerült felkeltenem az érdeklődést, és hadd mondjam el, hogy eredetileg ezt a programot angol nyelven hirdettük meg, so let me ask, if there is anybody in this room who can understand or follow this program only in English, so would it be a problem if most of the speakers would talk in Hungarian? I cannot see anybody. So maybe the first talk will be in English because the speaker announced that tehát az első adás az angolul lesz, mert az előadó azt mondta, hogy ő angol nyelvű környezetben dolgozik, és neki ez egy könnyebbség lenne. És hát ezt követően nem egy kávészünetre kerülne sor, hanem egy kiadós ebédszünetre és kávészünetre. Ennek az a magyarázata, hogy a délelőtti programot, a kiállítás megnyitót követően nem valósult meg a fogadás a Krúdi teremben, aminek az volt az oka, hogy valahol a megrendelőnk, amit még december elején postáztunk az akadémiai klubnak, elakadt és nem érkezett célba. Úgyhogy ennek hiányában az akadémiai klub nem készült ebéddel, de már készítik az ebédet, és azt ígérték, hogy 13 óra 30-kor megnyílnak a Krúdi teremnek az ajtajai, és mindenkit, aki itt jelen van a teremben, szeretettel látok vendégül, hívok, hogy vegyen részt ezen az ebéden. Tehát az első előadást követően lesz egy 1 órás kávé és ebédszünet, és azt követően pedig a 3 előadás szünetmentesen tart végkimerülésig. Úgyhogy ehhez kérem mindenkinek a segítségét és a támogatását. És akkor felkérem az első előadónkat, akinek az előadásának a címe is talán rendelkezésünkre áll. Nem. Tehát Christ Miranda, The Structure of Relation Decoding Linear Operators in Large Language Models. This is going to be the title of her talk. So, I invite our speaker. The floor is yours.
So, hi everyone, my name is Miranda Christ. I'm currently a freshman at UC Berkeley. Today I'm here to present our paper titled The Structure of Relation Decoding Linear Operators in Large Language Models. This is a joint work with Adrián Csiszári, Gergely Becsó, and Dániel Varga. We have all worked on this together at our time at the Alfred Rényi Institute of Mathematics, the AI research group. And we all presented this paper in San Diego this year at the Neural Information Processing Systems Conference, which is a flagship AI conference. So at NeurIPS and Berkeley as well, many people told me that the title of this paper is rather complicated. Of course, I agree, this is true, but it's also true that, that if someone has a clear understanding, or at least an intuition behind what this title means, it actually means that they actually understand the paper itself, or like at least know what it's about. So my goal here today will be to give you a basic understanding of what do we mean by the structure of relation decoding linear operators in large language models. Oh, lovely. First, let's speak about language models. So the notion of language models has been around for a while. It has quite a bit of history in computational linguistics. It's really just the concept of having a probabilistic model in language. What do we mean by this? We basically mean that we use this theoretical tool to just help us reason about language. So we would like to know how likely certain words or phrases are to appear. For example, how likely the sentence "Paris is the capital city of France" appears in language. There's a special types of language models. They are called autoregressive models that basically predict the future based on the past. What this means is that we are trying to predict, for example, in the "Paris is the capital city of France" sentence, from the sentence "Paris is the capital city of France," we would like to only predict the next word, which is France. So as I mentioned, this was only a theoretical tool at first. No one really believed that this could be something big, because it's really only just statistics and calculating probabilities. But actually, around 7 years ago, something changed and quite remarkable happened, because researchers started to scale up these language models massively. They first scaled up the data. They started to train gigantic tens and even hundreds of millions, billions of parameter models on the whole internet and even more. And they actually did this with a specific artificial neural network architecture. So now, what will be the next word in "Paris is the capital city of" actually depends on the parameters of this huge architecture. This is how we got to today's language models, actually. And as we can see and as we know, it's really not just what we train to do. The capabilities that have really went above what we expected, just predicting the next word. So this specific neural network architecture is called the transformer architecture. The transformer architecture is actually the subject of our investigation in our paper. So I will provide you now a brief overview of it, just an intuition. I think it's crucial to at least have an intuition to understand our paper. So when we work with transformer architectures, of course, at first we have an input text. Here the text is "the capital city of France is," and we would like to predict the word Paris. Working with transformers always starts by just chopping up the world into pieces. These pieces are called tokens. And these tokens are actually embedded in a latent representation so that the transformer can actually work with it. These are called token embeddings. After embedding, the tokens will pass through the transformer model. Then, using a head, we will be able to just read out the probabilities of the words, so we can actually see that Paris will be the answer. The capital city of France is Paris. But let's look into transformers a bit more. As you can see, they are actually built with the same and completely identical transformer blocks, many of them. These transformer blocks are really important because stacking is a clear idea here. Each transformer block, as we go in the transformer, it actually refines and gathers information in order to predict the next word. If we look into them a bit more, as I mentioned, there's a gathering and a refining part. The gathering part is called attention. Attention is, I think I will give you an intuition behind attention. Let's just take the sentence, the dog got the ball and it was fast. Let's think about the word it in this sentence. If we just look at the word it itself, we don't really know what it means. And if we're processing the current word it's not really clear. So attention will try to gather information from the context in order to understand what it means. The idea behind this is that it actually computes similarities. So whether each token is similar to the word it. Some tokens will be similar, some will be not. But which is similar, which will be dog, it actually tells us quite a bit about what the word it means in this context. The other main part of the transformer blocks are feed-forward neural networks that actually process the information and refines them, transforms them into a more useful representation of what the attention gathered. So the intuition behind large language models is that we have an embedding to represent the elements of our language. Attention will gather information, decide what matters, and the feed-forward network will actually refine and transform this representation. While we are doing this many, many times, this is the stacking. So we will gather, refine again. And this way, when we are ready, we will be able to read out the next token using the head, which will translate back to our language. So this is what we have already seen. This is like what we get using the simple idea of predicting the next word, large language models. And we can, as I told you, and of course this has gone like way beyond what we expected to do. Now we can ask them to like explain the 6-7 joke or quiz us at the history of the Hungarian Academy of Sciences. If you're working, they're also useful. They can use to, for example, debug our code. So just to see where we are in our goal today to help you understand the title, you have already understood what we mean by large language models, or like at least the intuition behind it. So we are great. It sounds like we fully understand large language models, right? We have provided the data, train the models, and they can do many, many things, even things that we didn't think they will do. And actually we don't, because what we specified is only the architecture to learn it, the data that it can use to learn it, and what is it? It is the goal. It is the goal of what should it learn? It should learn to predict the next word. After this, the capabilities we see today only emerge because of these goals. So after providing these, we actually just let the model to find its own solution. And actually, there's a whole field of machine learning called interpretability, which aims to understand what happens really inside of these models and like really like what happens on the inside. How do they work? How can they predict the next word? And our paper is similar. Our paper is also an interpretability paper, and we decided to make like a step towards understanding what happens to the vast amount of information that large language models encode, because of course they do encode a vast amount of like factual and conceptual knowledge. Our way to think about this knowledge is through relations. To understand relations, let's take the sentences. Paris is the capital city of France. We have already seen this sentence. This is actually a sentence where two concepts are basically connected by a linguistic predicate. This is what we will call a relation, this linguistic predicate. So we have the subject, Paris, object, France, and the thing that connects them will be the relation. So we will work with these subject, relation, object triplets. Paris, capital city, country, France. But we can also have many subject-object pairs. So we can also say Rome is the capital city of Italy, Rome, capital city, Italy. But also, we don't really have to just speak about the capital cities. We can also speak about which food is from a country. So for example, sushi is a fruit from Japan, sushi fruit country. Sushi fruit from country, Japan. So our data set looks like this. We have many, many relations like country, capital, city, and food from country. And for each of them, we actually listed we actually listed what we call samples. Samples are the subject-object pairs, and they correspond to one relation. So, just to see, now we have already understood what do I mean when I say relations. Linear relation decoders also work on relations. What they are basically a matrix. They are a matrix that can map the subject embedding to the object embeddings linearly. How we did it is that by using a large language models, we are going to just perform next token prediction. So we have the relation and the subject. The capital city of France is, and we would like to predict the object, Paris. How we will do this is that we will start doing the next token prediction, but at some point, actually from very early on in the transformer, for example, after the 7th transformer block, we will actually take out the embeddings of the subject. After this, we will take the linear relation decoder and use it to map it to the first token of the object. This is, many people I have told this actually think about this thing as an early exit, for example. Because, like we have the whole model, it's like gigantic, as I told you. But what we are doing is we're not really using the end part, only the beginning, and just linearly map. There are two really important things about these relation decoders. First, that they are relation specific. What I mean by relation specific is that, for example, if we would like to know the capital city of France, we would need to approximate a relation decoder that can tell you what a capital city is of a country. But for example, if we would like to know something about foods, where is this food from? We would need to approximate another relation decoder for that. The second important thing in this is actually emerges from the first, that one relation decoder is actually more than 60 million parameters. This is because these relation decoders are D by D matrices, as I told you, D being the embedding dimension of the transformer, which is, to be precise, 4096. So it is quite clear that as the number of relations increases, the number of decoders, so the number of parameters increases quite substantially. So now, in the title, we already know what we mean by relation decoding linear operators, because they are indeed simple linear relation decoders. So our paper differs from previous papers in a quite big thing, that these linear relation decoders have been only studied like separately. So many people said things about a simple relation decoder, but no one really handled them collectively. And we wanted to change that. This really makes sense because we would like to say something about the structure of how the knowledge is organized inside of language models. So it is quite intuitive to look at the whole thing together. So what we did is we tried to handle them collectively. And at first, we investigated, like, how do these collections of relations relate? Can we compress them, for example? Or even, just let me be wild for a second, can we even model them? Like, when I say modeling, I mean, is there a way that, for example, we can generalize across these relation decoders? And it might not be clear, but this has actually everything to do with the structure of these linear relation decoders. Because if we are able to build an architecture that is able to take in a relation embedding, a vector, and produce a decoder, which is a matrix, if this is possible, and this is possible for relations that we have never seen before, that says a lot about the structure, because it means that there is a very strong and simple underlying structure. So of course, to be able to do this and model these, we actually need architectures to model this with, and an architecture that I can give a vector and get back a matrix. We chose order 3 tensor networks to do this. First, I will tell you a bit about tensor networks. We use tensor networks to represent, we can actually draw tensor networks using tensor diagrams. In each tensor diagram, you can see dots that are tensors, legs that are axes, and labels are the corresponding dimensions of that indices. For example, let's just take a vector. What you can see here is a vector that is a 1 by d2 vector. And if we take, for example, the outer product of this vector and the vector that is a 1 by d1 vector, we can actually get a matrix, M. We can also, using tensor diagrams, we can also draw a matrix vector multiplication. What we did here is that we connected the d2 leg of vector v and matrix 1 and matrix 1. And just connected them, and this has a special word for it, a special term. This is called contracting over D2. Contracting will be quite important. We will do the same thing. Here you can also see what happens or how to draw, for example, like matrix multiplications. Another important definition is the order of a tensor. Order of the tensors are basically the number of free legs they have. So an order 1 tensor would be a vector, an order 2 tensor would be a matrix, and an order 3 tensor would look something like this. This is actually the same architecture we used. As you can see, these are the models these are the architectures that we are modeling the relation decoders. We have a subject, a relation, and an object leg, and how we will use it is that we take the relation embedding and contract it over the relation leg. And as a result, we will get a matrix that we can just take out, and this matrix will be the simple linear relation decoder for the corresponding relation. So, as I told you, as I previously have seen on the figure, we will give a vector, and we will just get a matrix. We also experimented using slightly different tensor network architectures. Here you can see them. It's like overall 4. And now we're actually ready to ask our first question. Can we handle relation decoders collectively by compressing them effectively? This is quite a reasonable first question because compressing sounded like a doable thing. What I would also like to tell you about tensor networks is that they're really probably the most simplest architecture we can use to achieve this whole thing. It might not seem important that they are really simple. Why didn't you use just simple neural networks to do this? But it actually makes sense, because we would like to say something about the structure of relation decoding linear operators, which means when we speak about the structure and we try to model the structure, we are at first trying to do this with the most simple architecture possible, because the simplest the architecture is, the stronger the underlying representation must be. So if we are able to linearly, with linear order 3 tensor networks model our collection of relation decoders, that means they have a clear underlying structure. So this was our first question, as I told you, and we have concluded that these linear relation decoders are substantially compressible. At first, we needed a measure of performance. This is faithfulness. This is actually what previous work used to evaluate these relation decoders. You should think about it as an accuracy on the object predictions. So we will just do next token prediction, apply the relation decoder. We will get just a prediction, and then we will compare whether it's the same as the target, and this is what faithfulness does. So here you can see our results. Our baselines are basically low-rank baselines. Also, I would like to mention, is there a laser I can use? Okay, it doesn't matter. So as you can see, the results are for us almost perfect and we have decreased the parameter count several orders of magnitude. Our baselines are actually low-rank baselines. We came up with these. But we also had an original baseline, which is basically just stacking the relation decoders together and just average their faithfulness, see how they do. They wouldn't really fit on this slide, actually, because if we just take generally the relation decoders themselves, they actually only achieve around an 0.4 average faithfulness. So these results are like really surprising, because we didn't just decrease the parameter count, we also achieved much better results. So of course this raises questions. Why are they so substantially compressible? And of course this can be true because they have a very strong underlying semantic structure. So we started to investigate whether this is true. And how we did this by providing a cross-evaluation protocol. So what we do is basically take every decoder, and evaluate it on every relation. For example, if we were to cross-evaluate country, capital, city, and food from country, then we would apply the food from country decoder to the samples of country, capital, city, and vice versa. This shouldn't work. The thing is, this whole thing, it should yield results that is like a diagonal cross-evaluation matrix. This is a cross-evaluation matrix. On the y-axis, you can see the relation themselves, and on the x-axis, you can see what the decoders were, like actually were. And as I told you, it was previously thought that these decoders are actually relation-specific. The thing is, if that was true, this matrix would be a diagonal matrix completely. But as you can see, it has like a clear blocky structure. We have a block where all of the relations kind of are about gender or try to say something about gender. But we also have like a linguistic block or something. And we wanted to investigate whether this is just a coincidence, because originally the data set we used had like 47 relations, and we realized this blocky structure, but like while really just closely looking at the relations, what performs good on what's not was trained on, and etc. So we actually decided to extend the whole data set. We provided an additional around 50 samples, and we were careful in these to incorporate different relations, but still it could have had like some blocks. For example, the first block is all about antonyms. What's the antonym of a noun? What's like, for example, an antonym of like a computing concept? And also on the other, we can see countries. That is actually our country block. As you can see, this also includes like food from country and primary language spoken in country, or capital city of country that I already mentioned. So it doesn't really matter which decoder we apply to which relation, because it kind of performs the same. So this is basically one of our like biggest conclusions, that it was previously thought that linear relation decoders are relation specific, but we realized that they are primarily like property based and really just capture something bigger. Like if you think about it, it kind of makes sense, because why would you need two different things, or even five different things, to just read out the same thing, country? What is Paris is the capital city of France. Sushi is a food from Japan. You're really just reading out countries. So this really makes sense that you don't really need different things to do that. So our final question was what I told you about when I spoke about modeling these relation decoders, whether linear relation decoders are generalizable, and whether we can generalize using tensor networks. We observed more types of generalization. The first is sample-wise generalization. Just to recall, a sample for a given relation are its corresponding subject-object pairs. So it will be Rome and Italy, Paris and France. This is just a sanity check. This is really important because we would like to see whether our tensor network actually learned the relation themselves, or the knowledge that was inside the linear relation decoder, or just started to memorize. And actually, we have concluded that the results are comparable, and in most of the cases actually better than linear relation decoders. So this sanity check was successful. There is sample-wise generalization. And then we can actually get to the interesting part, which is held-out relations. So What we do here is we just train the tensor networks using some relations, using some relations, but we also just leave out a test set, just leave out some to test whether our tensor network can actually perform well on the relations they have never seen before. And here you can see our results. The blue bars are for the train set, the purple ones are for the test set. As you can see, it sometimes works, but in most cases, it kind of doesn't. Certainly, something is happening. So we actually started to look at these bars one by one. What is the purple bar that is almost, that is exactly as tall as the blue one, and how did that work? And this is actually because they are corresponding to one property. So the 3 bars you can see there are the country currency, country largest city, and primary language spoken in a country. So it is rather clear, but is also intuitively right, that if we have a property that is represented in the train set and the test set as well, we will have generalization capabilities. If it's not, then we won't. Because just think about it, like, why would we? If we learn to read out country, why would we be able to read out color as well? But if we learn to read out country on some things, we are going to be able to read out countries on something we have never seen before. You can also see, for example, year properties. So when was a famous person, when was a famous king get their crown, or when was someone born? All just years. So we had this idea, this intuition that I told you, that if a property is represented in a train and test set as well, we actually do expect generalization, because why would it not? And actually, this is true. As you can see on this figure, we have like a 99.1% generalization. And I have to tell you about these relations that they are all corresponding to the same one property. This property is like simple arithmetic Operations. We actually created this data set as well. It contains relations like number +1, number +3, and so on. It makes sense that we are able to read out these numbers as well. And that is why this really supports our hypothesis that we can generalize with tensor networks when we have properties, and it also supports that these are indeed properties, not just relation-specific samples. So I think we're pretty close to the end, because at first I told you about large language models, then you understood relations and simple linear relation decoders, and now I actually told you about what do we mean by the structure. How there's a very clear underlying structure. So how we could at first compress the relation decoders, then realize that they are not really something that we thought they are, but slightly different. They aren't relation specific, they're property centric. And then I showed you examples on how we can actually generalize across them, and how they sometimes perfectly generalize. So I can say that I think now you have an understanding of what we mean by the structure of relation decoding linear operators in large language models. Thanks.